Our next lesson is called stretching and shrinking functions. So you're going to start with an opening exercise. It says consider the function f of x equals the absolute value of x. So I want you to think back to vocabulary we've learned before. This would be considered your parent function, where you start and what you compare everything to. Complete the following table of values for each transformation and for the parent function f. Then graph the equations y equals g of x, y equals h of x, y equals j of x, and y equals k of x on the same coordinate as the graph of y equals f of x. Label each graph. So at this time, I want you to complete the opening exercise. Please use your graphing calculator to help you do this. It can help you with your table of values quickly, and you can see for sure whether the graphs you are sketching are correct. When you are ready to resume after doing the opening exercise, then please unpause the video. Okay, now you've had time to try the opening exercise. Let's take a look at the answers. You can use your graphing calculator to get these table of values. So remember that you can do kind of a replacement situation here, where if it's 2 times f of x, that's the same as 2 times the absolute value of x. This is 0.5 times the absolute value of x. You just do the substitution. And this is negative 2 times the absolute value of x, if you actually take f of x and put it in that spot. So then there is my table, and then here's a picture of what your graph should look like. So you can see which one's got wider, which one's got skinnier, and you can see that one was also reflected. So we're going to take and summarize everything that we've seen by looking at this opening exercise. So double check your tables and your graphs right now, and then when you're ready, move on to the next part of the lesson. Okay, so now in part A, it says using the results from the opening exercise, describe how the graph of y equals k times f of x, so we're multiplying here, relates to the graph of y equals f of x for each of the following cases. So we're basically going back to revisit what happens when you multiply a function, how it vertically stretches it or shrinks it. So that's what we're going back to look at today. So in situation 1, if k is greater than 1, so if we go back and look at our picture, k is greater than 1 is looking at h of x. H of x we multiplied by a 2 on the outside. That's the graph that's teal. So compared to the green graph, which is my parent function, you can see it became skinnier, which means we vertically stretched it. And you can also remember that from previous lessons. When you have a number bigger than 1, it's a vertical stretch. So vertical stretch, because it's on the outside and it's bigger than 1, by scale factor k. Okay, and then in parentheses, we're going to put the example from our front page so that you can refer to it. So this is referring to h of x, where we doubled on the outside f of x. Now the next one, part 2, is when it's between 0 and 1. So we have an example of that. If I go back and look at j of x is in pink, and we multiplied by 0.5, which is between 0 and 1. So if I look at green compared to pink, you can see that it got wider, which means it was actually a vertical shrink. Remember what I said to think about dough. You took your hand and you flattened it on the top. So in number 2, because it's on the outside and it's a number between 0 and 1, it is a vertical shrink this time by scale factor k. So again, on the outside, we'll put what one we're referring to. J of x was equal to 0.5 times f of x. So that's the one you want to refer to. Now we have k equals -1. So we don't have one specifically that was multiplied just by a -1. But if we do look at k of x, it was multiplied by a negative, and you can see that it was flipped over the x-axis. So that would be a reflection over the x-axis. When you look at -1 less than k is less than 0. Again, we don't have one on the front that directly relates to that, but thinking about what we learned already, we have a negative number, so we know it's going to reflect over the x-axis. So reflection over the x-axis, because it's on the outside, being multiplied by a negative. But because it's between 0 and -1, it's also a vertical shrink. So vertical shrink by scale factor. Okay, so that's both of them together. And then if we look at k is less than -1, that actually relates back to our k of x. So if we go back and look, k of x multiplied by a -2 on the outside. So you can see when we look at it, it's skinnier than the green, which means it's been vertically stretched. And it's also been reflected over the x-axis because of the negative. So here we will have reflection over the x-axis because of the fact that it's negative. But we will also have a vertical stretch by scale factor k, because of the fact that it's less than a -1. So this is referring to our example of k of x, which was equal to -2 times f of x. Now, when we were filling out this chart, we were looking at the values, whether they were larger than 1, between 0 and 1. And so what we're seeing here is that we can tell by looking at the equation. Well, let's go back and take a look at the graph and see how we can also tell by looking at the table of values, because this is going to be helpful when you go on and start working on your practice. If I look at the table of values for these, you want to pay attention to how it is affecting your numbers. So if I look at the original parent function right here as f of x, when I look at h of x, which we multiplied by a 2 on the outside, let's look at the values that we get. We get 84048. So what happened is your output values for f of x were multiplied by 2 to get your output values for h of x. So let's say we didn't know the equation was 2 times f of x. It's very helpful to write down tables of values, even if you haven't been asked to do so, in order to compare them. So I would have written down, I would have looked at my graph and picked points off the graph to make a table. I would have done the same thing for h of x, and I would have looked to see how my output values changed. My output values changed because I multiplied by on the outside, which we'll see eventually. But if my output values are changing, that tells me that something has happened vertically because it affected the output. And then I can easily see that it was multiplied by 2, and I would be able to come up with that equation that it's 2 times the absolute value of x. So use those table of values to help you figure out what the equations should be. At this time, there are practice questions that can be completed for this lesson. So what you're going to want to do is pause this video and do the practice questions. Now, if your teacher has given you a separate practice activity, you are done with this video and you should just end and go complete your practice. If they want you to complete the practices within the notes, please pause the video, complete the practice questions, and then resume the video when you're ready to go over them. Another option would be that after you complete your teacher's practice separate activity, you could watch the remaining parts of the video to hear explanations if you struggled with any of the questions. Okay, so now to go over the practice questions. The first part said describe the transformation of the graph of f that results in the graphs of g, h, and k given the following formulas for each function. So number 1, the parent function is f of x equals x cubed. So when I look at A, it's been multiplied on the outside, so I know that's a vertical stretch of 2. B has been multiplied on the outside by a 0.5, so that is a vertical stretch of 0.5. And C, we were multiplied by a -3, so 2 things have happened. It was reflected over the x-axis and a vertical stretch of 3. In number 2, your parent function is the cube root of x. So you had to create tables of values for each, which you should have used your graphing calculator to help you do. So green was my parent function, and you'll see that I added -8, -2, and 8, 2, so that it created a graph that was easier to create, so I didn't have to plot those kind of difficult decimals. Underneath g of x, you can see since we multiplied on the outside by a 2, all of my output values of f of x were multiplied by 2 to get my output values for g of x. Now, if we look at h of x, it's different because we multiply, if you look, on the inside, so that means we multiply the input by 2. Okay, so then I went over to the side and graphed it, and you can see how it affects the graph for each one. So looking at y equals g of x, we had a multiplying of 2 on the outside, so you can see it's a vertical stretch of 2. When we look at y equals h of x, we have a multiplication of 2 happening on the inside. So remember, when it happens on the inside, it's a horizontal change, and it's the opposite of what you see on the inside. So if I actually see a 2, that means my shrink should be of 1/2. So again, because it's on the inside, it's horizontal. Because it's a positive 2 on the inside, it acts the opposite, so it's actually going to be a shrink of 1/2. For question 3, you had to identify the parent function. How does the translated graph relate to the graph of the parent function? And write the formula. So I've done each one in each section. The pink or red line is your parent function. I made a really quick key point, 1, 1 in the table, so I could take a look at what happens and how it changed. If I look at the purple, h of x, if I wrote down where my y value was at 1, I'm at 0.5, so you can see the output was multiplied by 1/2. So my equation should be h of x equals 0.5 times the square root of x, which would be a vertical shrink of 1/2. So I'm answering the second question and the third question kind of at the same time there. Then at the blue line that you see, g of x, I wrote down again the critical point of where y is when x is 1, and I get 1, 3. So I can see that the output was multiplied by 3. So that means g of x is 3 times the square root of x, which means it's a vertical stretch of 3. Notice it's important to find a key point and use the table to assist you in writing these. Now looking at number 4, same questions. We want to know what's the parent function. So again, I can tell by the U shape that it's going to be f of x equals x squared. How does the translated graph relate to the graph of the parent function? So we're going to look at each one, and you can see by my labeling that I've identified some key points. So let's start with h of x, which is the wide arc that I've drawn here in blue. If I look at this, I want to write down a table of values that shows what is going on compared to the original y equals f of x. So in pink is the parent function y equals f of x. You can see a table for that on the left-hand side. The table will help me compare these other functions to figure out the equation. So when I compare these certain values for h of x, I see that my output for 4, let's look at 4 as an example. Originally, 4's output was 16. Now for h of x, 4's output is a 1. So I'm taking 1/16 of my output in order to get h of x. So you can see that I've multiplied by 1/16 on the outside, which means that this is a vertical shrink of 1/16. When we look at the purple upside down arc compared to our pink y equals f of x parent function, again comparing the tables of values and noticing that it looks like it has been flipped upside down. When I look at my table values, let's see, an input of 2 had an output of 4 originally. Now an input of 2 has an output of -8. So we can tell that the output has been multiplied by 2. And because it's upside down, it's been reflected, which means I need to multiply by a negative, which you can also tell by the table with the negative values. So my equation for g of x should be -2x squared, which is a reflection over the x-axis and a vertical stretch of 2. Now for practice exercises 5 through 7, which concentrates on translating functions. I wrote at the top to make sure that you change the letter of the function each time. That applies for the earlier questions as well. Hopefully you've noticed that. If you're going to call the parent function f of x, then every subsequential function that you create should be using a different letter for each one, and you'll see me demonstrate that in these practice problems. So in number 5, it says for each of the following graphs, use the formula of the parent function f to write the formula of the translated functions. For number 5, the top one in part A, the middle function, the black one, is f of x. I called the teal one that is above that g of x, and the green one below it h of x. So if I'm looking at the teal one, I'm going to pick a critical point. You can see there it says identify a key point. I'm going to follow that point to help me figure out the transformations. So I can see with g of x, or the teal one, that I've translated up 2.5 units. So that means I should be adding 2.5 on the outside. So g of x should be the absolute value of x plus 2.5. For h of x, the green one that's below the parent function, it is translated down 4 units. So I'm going to subtract 4 on the outside for h of x equals the absolute value of x minus 4. Looking at graph B, our parent function here is the cube root function. So f of x equals the cube root of x. Again, I picked a critical point for all 3 of the functions so I could follow that point around. So in red, which is actually the lowest graph there, f of x, I see that in order to get the blue one, which is g of x, I translated up 1. So I'm going to write plus 1 on the outside. So g of x should be the cube root of x plus 1. Make sure you can clearly tell that the plus 1 is outside of the square root. When I look at the one in purple, which is labeled as h of x, I see that that translated 5 units to the left. So remember, right and left is a horizontal change, so that means it needs to go inside. And it's the opposite of what you would think. So usually left 5 means subtract 5. That means we're going to add 5. So we should be adding 5 underneath the cube root. So h of x equals the cube root of x plus 5. Then, in number 6, this is a piecewise function whose domain is -5 is less than x is less than 3. We had to sketch the graph of the given functions on the same coordinate plane and label your graphs correctly. So the first thing you want to do is look at those 2 functions and decide what transformations have actually happened. If I look at g of x, we've added 3 on the outside of f of x, which means I need to translate up 3. For h of x, we've subtracted 4, but it's on the inside, so it acts the opposite of what our gut tells us. That means we're going to translate to the right 4. Now, when you go to create the sketch, it's helpful to identify some key points. So there's actually 4 key points I feel like were helpful to create these graphs, and you can see them there on the original f of x parent function. And then I can take each of those points and translate them accordingly to what I decided when I looked at the functions. Lastly, for number 7, it says match the correct equation and description of the function with the given graphs. So the equation labeled with either E1, E2, E3, and E4, and then the description with D1 through D4. So first thing you want to think about is whether or not it's got a negative A value. If it does, it should open down. So that's important to take a look at. F of x at the top there should be E3 and D2. G of x should be E1 and D4. H of x should be E4 and D3. And P of x should be E2 and D1. You can see that I found the critical point. I'll use h of x here. I know the original parent function of x squared is at 0, 0, so you can see I marked it. And then I marked that critical point, which is the vertex again, in all my other functions to figure out where it went. Did it go up and left, down and right, etc. You can also use these equations to double check tables of values and take a look at where the turning point or vertex of these graphs are. And that concludes your lesson on stretching and shrinking functions.